Okay, so before, in the last end of the last video, we said we wanted to work on this mechanism here. So I'm curious if I turn on my, can you see me, or can you see my camera? Like my writing camera? Excellent. So I'm going to write this down and then I'll just switch purely to camera. That way you can see it clearly instead of share screen. And now we're going to have HCl. So here's my hint for you when you are doing mechanisms. When you're drawing a problem like this, are you guys going to have it online or is it going to be in person?
Online.
Okay. But when you are doing a mechanism, always draw your starting material and then draw your product. Matthew, do you know why you want to do your problem like this?
So you can see where you're trying to, the answer
Yes,
you're trying to get to.
Your steps should always try and get you closer to where you're going. So I've written this down and I'm going to pop out here. I'm going to stop share. So hopefully if I pin myself, spotlight for, okay, so can you see this clearly? Put this down ever so slightly. All right, so whenever I have an acid over my arrow, this is HCl, HBr, whatever, my acid is always a catalyst, meaning it should usually be involved in my first step. Acid-base chemistry is really fast. So what's the only thing here in my starting material that can grab that proton?
The OH.
Not the OH, but
Oxygen?
more specifically.
The oxygen?
The oxygen's lone pair, right? It is going to grab like this. And then this is going to go back onto the chlorine like that. Okay. So now I'm going to end up with this wonderful little cyclobutyl group. To here, here, and then I'm going to have oxygen to one hydrogen, second hydrogen, lone pair. This is going to be a plus charge. Now, this is something I always do in my mind. Keep track of your counter ions. I always keep track of them like this because I don't know when I'm going to need them again, but I'm going to write it down there because I know that it's in the problem. Because if you remember back to my rules of mechanisms and arrow pushings, we always want to conserve charge. So when we started, these are both neutral, right? The overall charges add up to 0. There's no charges. But now I have an O plus and a Cl minus. Those add up to 0. So I know my charges are balanced. All right, so now I have made a good leaving group. So this is an SN1 reaction, but what, Gwen, do you have any idea what is a good indication that this is an SN1 reaction? Think about your starting product and your ending product. There's a R term that happens. Whenever you see a rearrangement that comes about from SN1 reactions, whenever you see that your starting material does not represent, it does not look like your ending material, meaning something has changed, you have moved about methyls, you have gone from a 4-membered ring to a 5-membered ring, that means that you have to form a carbocation, and you get that from SN1. You could have a rearrangement, it could be E1, but Matthew, how can you tell that this is not an E1 reaction? What about your product tells you that this is not an elimination?
Because the OH was replaced by the Cl.
In an E reaction, what do you always form? E reactions always form alkenes, right? In an elimination reaction, you would always form a double bond. So you form a carbocation in S1 and E1. That's when you have rearrangements that are possible. But in my product, I don't have a double bond. So I know that it has to be an S1. That is your key indicator here. So now, in an SN1 reaction, my leaving group is simply going to pop off like that. So now I'm going to be left with the cyclobutyl group. And coming up to here and here, this is my new carbocation. I have a water molecule that has popped off, and I have a chlorine molecule like this. So my charges are still balanced. I have a water molecule, and I have a carbocation. So now the question becomes, Mag, what type of carbocation is this? Primary, secondary, or tertiary?
It is secondary.
Yep, secondary carbocations are not great. So we are going to take a small side trip here, and we're going to tell you when you should do a carbocation rearrangement. This is how you tell when 3 different types of carbocation rearrangements happen. We'll come back to this mechanism in 1 second, but this is something that I think might be important. So if you form a secondary carbocation next to a tertiary carbon, such as here, or if you form a secondary carbocation next to a quaternary, such as here. So these are 2 very common situations when you form secondary carbocations. So if you form a secondary carbocation, Gwen, what should you automatically think happens? What's the R word you should think that could happen here?
Rearrangement.
Rearrangement, right? So you take a look and say I have a secondary carbocation. If it's only next to secondary and primary carbons, then don't worry about it. You can't have a rearrangement because it's not going to happen. But if you have a secondary next to a tertiary, you will always have what is called a hydride shift. Essentially, a hydride, so the hydrogen and the bond on the tertiary carbon are going to move to where that carbocation is at. So now your carbocation will be on this carbon, and you will now have a tertiary carbocation like that. If you have a secondary carbocation next to a quaternary carbon, one of your methyls is going to shift, and we call that a methyl shift. And so now, this, and our carbocation has again shifted. So we have rearranged. So if you have a secondary carbocation next to a tertiary carbon, you move over a hydride, that's the hydrogen with the bond. If you have a secondary carbocation next to a quaternary, you move one of the methyl groups. Does that make sense? Okay. So now, the last one, the trickiest of our shifts. Remember when you guys learned about rings and ring expansion, or you learned about rings and like stable? What number of carbons do you need to have in a ring for it to be relatively stable? What's the ideal number of carbons?
6.
All right, and what's the other one? 5. 6 is really stable. 5 is good. It's not as stable as 6, but it's good. If you have a 3 or 4 membered ring, they're not ideal. So if you form a secondary, hint, 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 carbon next to a secondary next to a 4-membered ring, you have what we call a ring expansion. Have you guys talked about ring expansions? Okay, well, it's on our practice exam here. So this is really simple. I promise you, it's not so bad. But if you have a secondary next to a 4-membered ring, we have a ring expansion. So these are the 3 scenarios for our carbocation rearrangements, all right? So we'll hop back to the previous problem and we'll talk about what's going to happen. She may talk about it with you guys, so let's just spend a quick minute on it. And if she does, you're prepared for it now. If not, it's in the back of your head because it will pop up at some point. So going back to our wonderful problem. What happens is that we have this secondary, and this is a tertiary right here. One of these bonds just goes like that. You can think of it as, and I'm going to change my camera real quick so I can. So you can think of it as my bond just going like, so it's like, so the bond is just shifting over like that. Right, so now if I go back to this problem, that's a great picture to freeze on. This bond is just going to shift here like this. So now I'm going to put a circle around the carbocation and I'm going to put a square where the bond used to be. We go from a 4-membered ring to a 5-membered ring. So now this was the original where the bond went. And then now this is the, here, this is where that was at. And now we have this one like this. So this is our carbocation because that's the carbon that lost its bond, all right? But now, what type of carbon mag is this carbocation?
Yeah. Secondary.
Mm-hmm. And what type of carbon is it next to?
A primary.
Nope, this one here.
Oh, secondary.
Nope, 1, 2, 3.
Oh.
This is a tertiary. So if you have a secondary carbocation next to a tertiary, what do you have happen according to our wonderful list?
Hydride shift.
Yep, so the hydrogen that is here is just going to pop over. Then we end up with this now, where we now have a tertiary carbocation. And then our chlorine, which has just been chilling out, comes and attacks like that, and we get our final product. This is as tricky as it gets because you had 2 shifts here. You had a ring expansion followed by a hydride shift. This is as tricky as a problem gets. If you followed along, but you were a little unsure, that's a good place to be. If you are capable of doing it the entire way, you are better than you need to be. But if you could at least follow along and say, I understand kind of what's happening in each step, that's a good place to be. All right, so remember, just take your time and just think about every step that I do, am I getting one step closer to my end product? Right, so that's really the way you should think about it. Okay, so let's go back to our here, practice exam. All right. Okay, so predict the products for the following reaction. We have cis-1-bromo-3-methylcyclohexane, and we add NaSH acetone in acetone. So think about it, you guys, for 30 seconds, and I'm going to ask you to think about what type of reaction is happening here. SN1, SN2, E1, E2. Figure it out. What type of reaction is going to happen? Okay, so we have what type of carbon with our leaving group? Primary, secondary, or tertiary?
Is it secondary?
It is a secondary. So did you eliminate any of the reactions, or are they all still in play right now?
I think
They're also in play.
They're all still in play, but let's take a look at our next thing. We want to take a look at what's over the arrow. NaSH. Is this going to be strong or weak?
Strong.
Remember, if we see a metal, the exception of that one that we did with the carboxylic acid, if you see a metal, you're going to assume that it's either going to be a strong nucleophile or a strong base. Okay, now SH minus, nucleophile or base? Whenever you see an S minus, we should always think strong
Nucleophile.
nucleophile. SH minus is S minus is always going to be a strong nucleophile. But what is your last dead giveaway that this is SN2? Your solvent acetone is polar aprotic. That's an SN2 solvent. Also, look at your answers. Do any of your answers have double bonds? So it cannot be an elimination reaction. It has to be a substitution. So you might be saying to yourself, well, Dr. V, I've done all this stuff. Actually, I don't care if you call me doctor anymore. Terry, I've done all these things. What do I do now? The illusion of separation is gone. You can call me T-star, which is what my friends call me, my chemistry friends. It's a physical chemistry reference. It's the excited state. I'll let you piece together what that means. But essentially what happens here, what might be good is we know that we are reacting cis 1 bromo 3 methyl cyclohexane. All right, so, and I know that I'm reacting it with Na plus and SH minus. So what I'm going to do is that I'm going to pop out of here. And so what is useful for me is if I just take this and draw it out. So cyclohexane, 1, 2, 3, 4, 5, 6. I know on 1 I have a bromine, and on 3 I have a methyl. What's the relationship? Cis means they're what? Same direction or opposite direction? Right? So that means if the bromine is on a wedge, the methyl has to be on a wedge as well, right? Or I could easily draw this, and it's the same thing where the bromine is on a dash, but the methyl is on a dash as well, okay? So now I know that I am undergoing an SN2 reaction. This is going to replace my bromine. So when I do an SN2 reaction, do I get a split of products, or do I get the same stereocenter, or do I flip stereocenters, or do I get both stereocenters?
SN2 inverts.
Yep, SN2 inverts. So if I do this one, my CH3 is going to stay the same as a wedge as it started out, but now my SH is going to be on a dash, right? Or if I drew it the other way, again, my CH3, since that stereocenter is not involved, stays a dash, but now this would be a wedge. The important thing you should know is that since my leaving group and the other one are both start out the same way, my nucleophile now is going to be pointing the opposite direction of the group that was originally there. So going back to my problem. Oh, do you still need to see this for a second? Are you good? Question, Gwen.
Yeah. So the below the first one, that's the.
Oh, so these are the same things. It just depends on if I draw them wedges, both dashes, right?
Yeah,
My products could look like that. But the thing is, I see is that it doesn't matter really, just as long as my new nucleophile is pointing the opposite direction of my methyl group.
okay.
All right. So now, which of these is going to be the correct product?
Number. I want to say number 2. No, number 3.
Okay, so Matthew says 2, Gwen says 3. Mag, what do you say?
I think I'm in between 2 and 3.
Got to pick one.
Maybe 3.
So in an SN2 reaction, our nucleophile replaces what?
Oh, the house.
Oh, yeah.
The leaving group, right? That's why Matthew was correct. It's number 2. Yay.
Cool.
Don't forget your basic principles, right? Is your leaving group is always going to leave.
Okay.
So if that's your leaving group, make sure it is gone in the final product, right? I'm assuming next week, if I do this multiple days, I will see more of you because I only see some of you during until
No,
it's exam week,
Yeah.
which is fair. I mean, you guys are busy, so all right. Next one. Step 1, NAI and acetone. Step 2, NaCN and DMF. So, should give a clear? No. I think you can see all the answers. So, what are the answers for this one, or answer, depending on what's happening? I'll set this here for a minute or two, and I will draw out the problem and mechanism on my little notepad. I'll kill my camera so you can't see what I'm writing. It's going to be 80 degrees tomorrow, so I'm going to go down to the water with a book and read. Then I'm going to go to the Irish bar and grab a beer.
That sounds nice.
Okay, back to recording. So I will let you think about that, and I will draw out the mechanism for this one. So what's the key to this problem? What do you need to know for step 1 and step 2?
Whether or not it's a strong nucleophile, or like if it's a nucleophile or a base.
Yeah, you need to know whether or not it's an SN1, SN2, E1, or E2 type problem, right? That's the key to this. Okay. Do you guys have an answer?
I feel like 3 is one of them, but I'm not sure about the second part of the problem.
Well, you have to predict the products for both steps. So the ending product. You don't care about the intermediate. You just care about what your final product is.
So step 1, the first part, because I know it would have to flip, so it would have to go from dash to wedge.
So I would just say, do you guys have an answer real quick?
I'm gonna guess 3 and 4.
Okay, you're gonna say 3 and 4 are the answers. But remember I said there's only one answer here.
Oh, there is? Okay.
Because there are 2 steps, but you assume that both steps happen.
Okay. I'm gonna guess 4 then.
Yeah,
Okay,
I
4.
say 2 and 4.
2 and 4, okay. Max?
Mm,
So in our first step, NAI, it's a good nucleophile. Acetone is polar A product. This should be my dead giveaway that it's SN2. Sodium iodide, you could be kind of like, well, I guess it could be weaker, if you're unsure. But the fact that this is a polar aprotic solvent like acetone, that should be your dead giveaway that it's SN2. SN1s, remember, prefer polar protic. So things with alcohols or amines and stuff like that, OH&H. So SN2, my I is going to come in and replace my OTS, metosylate. And now my iodine is going to be on a wedge, okay, at the end of step 1. Step 2, sodium cyanide and DMF. Sodium cyanide, as we said, the sodium or nitrile, the CN minus, that is a strong nucleophile, right? And again, I look at my solvent, DMF, polar A product. This is a dead indicator that this is SN2. My CN is going to come and replace my iodine. Now it's just going to be on the dash. So I have back-to-back SN2 reactions. So you should only get one product. So your answer should be 3.
Wait, it should be 3?
Or, sorry, 4? Was it?
yeah, 4.
4, sorry.
No, yeah, that's actually what I was gonna ask. If there's 2 steps, if you would
You
have to,
just
like,
assume that all the reactions happen.
okay.
The way that my professor used to say it was just think of the steps of reaction as going down a staircase. Once you start falling down that staircase, you don't stop till you get to the end.
That's a good one.
So our final product should be this. I miss that old man. All of my professors are starting to pass on because I had old professors, so they're starting to die, unfortunately.
Oh,
They had good runs. They had quality students like me, as opposed to me, who has to deal with you guys. All right, so let's go back to our. All right, so here we have this now. So our answer should be 4, this one, CN. I think I told you when I went to go ask my physical chemistry instructor for a letter of recommendation for grad school, he asked where I was applying, and I told him, I said, I'm applying to these schools, Harvard, MIT, Purdue, and he was like, are you applying to Washington? And I said, no, because there's not really anyone here that I think I want to work with for graduate school. And so he said, so if I sign this letter of rec, this will guarantee that you have to leave the state of Washington. And I was like, yes. And he's like, well, then I'm going to write this letter today and write it excellently. It's like, I'll pretend that doesn't hurt. So I want you to know the abuse that I give you guys, I received it from my professors as well. So you're not special. I just make mine funny though, as opposed to abusive. Okay. What mechanism is the following reaction likely to occur? SN1, SN2, E1, E2. Put it all together, guys. I know you can do it. What type of reaction is happening? What's the first thing we look at in this type of reaction?
The sulfur.
I look at the carbon with my leaving group. What type of carbon is that?
Primary?
It is primary. So I know that that's going to eliminate E1. Right now, that's going to eliminate E1, and it's going to eliminate SN1. So now, since this is a primary, I only have SN2 and E2 left. All right, so now NaSH, as Matthew said, is that a nucleophile or a base?
Nucleophile.
Since it is a nucleophile, eliminates my elimination, it has to be SN2. And that's how easy it is. Just do it step by step. Don't try to rush through everything at once. Just think about what's happening. Question. I see it formulating.
I'm trying to think if I actually need to ask this question or if I'm just being stupid.
Just ask it.
So why did you eliminate E2?
So we eliminated E2 because NaSH, is this a good base or a good nucleophile?
Oh, nucleophile. Okay.
Because remember, to have elimination reactions, you need to have a good base.
And then it's a strong nucleophile, so that's why it's not SN1.
Well, also, this is a primary. This is the most important thing, right? That immediately eliminates SN1 and E1 if it's a primary. I am just going to scroll real quick because I'm curious to see how many more questions this thing is. Oof. That's right. Okay, based on this reaction, what type of reaction is likely to occur? SN1, SN2, E1, E2. If there's multiple possibilities, just think through it. Okay, so what type of carbon is my leaving group?
Primary.
So what can I eliminate?
SN1 and E1.
Yep. NAOME, good nucleophile, good base, both.
I think
Think to the beginning of this
It's-
evening.
Oh,
two.
can be both.
This is both. This is one of my exceptions, right? This is one of the ones, OME minus, OH minus, OET minus. These are the ones that are both nucleophiles, good bases, remember? So if you were asking me as a, what would you say, Terry? I would say SN2 is favored here, but to be safe, SN2 and E2 are both possible because there's no real distinction here. Because you can come in and eliminate here from this proton and form the double bond, or you can do an SN2. So I would say for if you have something like OME, the only way that there will be, if you have a methyl for your carbon, you will solely say SN2. If you have a tertiary, then you would solely say E2. That's the only time. If it's primary or secondary, then just throw both in there just to be safe. Does that make sense? How do you guys feel about that now? Now that I've showed you one of the many secrets of this, hopefully you're now aware, and hopefully maybe she'll throw something like that at you.
I hope the exam is really similar to this, because if it is, then I so far feel pretty
Same.
Okay, complete whether this is what type of reaction is here. So SN1,
I like
SN2, E1, E2. So what type of carbon is my leaving group attached to? So I'm going to write all of my things up here so we can see them.
tertiary?
Wouldn't it be primary? No.
Tertiary.
It is tertiary because it is
Yeah.
attached to 3 carbons. So since it is tertiary, can I eliminate anything?
SN2.
Yep, I can eliminate SN2. All right, so I've eliminated one thing. Now, water is this strong, weak, what?
It's a weak.
It's weak, so what can I eliminate? E2. E2 needs strong, right? So, can you eliminate any further, or is this it?
It's it.
This is it. SN1 and E1 are always in direct competition.
Oh, that's right.
So if you get down to this point, if it's a weak base, weak nucleophile, tertiary, if you can't distinguish, this is it. What was the only thing I told you that could push something towards elimination? Higher temperature.
Oh yeah, I've literally.
But I haven't seen anything like that in this test, so don't worry about it so far. So I haven't seen it, so maybe she hasn't taught you guys that, but that is something you can think about. If for some reason it does pop up where she mentions it.
Wait, did you say that water was a weak
Base and
Base.
weak nucleophile. Because is it neutral or is it charged?
neutral?
Neutral. So it is both a weak nucleophile and a weak base. Okay.
Oh, I was like, isn't that the same problem, but it's a different.
Now what's going to happen here? So I'm going to draw, what type of carbon do we have?
Tertiary.
Tertiary. So what can we eliminate?
SN2.
All right. Now NAOME, strong or weak?
Can it be both?
Both.
Is it strong or weak?
Weak. Strong.
It's strong, so that eliminates SN1, E1. It has to be E2. So just think about it in terms of, before you even get to the question of base or nucleophile, just think if it's strong or weak, because then that'll help aim me towards the right direction. So what's my only answer left is E2. All right, this is about to end. We'll come back for the last part of this. So I'm going to close this out and then we'll be back here in a quick minute.